Welcome back. Uh, so this was the last part which we were discussing about, that we need to have a complete and detailed mapping of the area surrounding or in the neighborhood of any uh, structure of interest. Okay. Similarly, here also in this uh, sketch, the part which has been shown, that how far the faults are present, uh, like in terms of the distance from the faults, sorry, that the structure is present uh, away from the fault, and what is the distance and what will be the source, expected source of the point where the energy will be released. And so the important part of this exercise is to understand that what will be the intensity of shaking from a given earthquake. Now, suppose uh, this is the surface area which has been shown here, and what we learn from this, and if you compare, this is the intensity of shaking, okay, and the red color is showing your high intensity. And point to be noted here is that in the epicentral area, the intensity is not so high, okay, it falls somewhere over here in this area, okay. Even this portion which is away is having comparatively high intensity, but these areas which are sitting away from the epicentral region are having much higher intensity. So this will depend on that what material you uh, you are having in that area, what type of lithology, what type of soil you are having, what type of rocks you are having. Based on that, you will experience the intensity of shaking. Okay. So when this type of exercise to produce the micro seismic zonation map. So microseismic zonation map includes the information of active faults, includes the information of earthquake, source of the earthquake, and plus the material which we say the site effects, okay, because that is going to talk about the site effects. So even if you are located, for example, located in the epicentral area, you are there, but the soil conditions are good or the rock conditions are there which are good, to which will result into the less amplification of the waves or maybe the intensity of shaking, you are safe. But if you are located even away from the epicentral region, but the site condition is ideal for amplifying the seismic waves, you may experience higher intensity of ground shaking. Another important part is that depending on the magnitude, how far will be the effect in terms of the surface faulting, and then the secondary evidence, okay. So this part will be after, we will talk about after the plate tectonic chapter or the plate tectonic lecture, where we will talk about the evidence signatures of, or the primary signatures and the secondary signatures, how we do that. So if you are having the primary structures or the primary evidence, we usually call the surface ruptures, okay. So surface faulting depends on that what is the magnitude. So larger the magnitude, one can expect that you have the larger rupture, okay. This 1,000-kilometer rupture is correlated with your 1964 Alaskan earthquake. And the threshold limit here, which has also been important for the liquefaction, is around 5.5 magnitude, okay. So this is the threshold limit where the liquefaction will be triggered in any area which is having ideal condition. Of course, it will not result into the effect of liquefaction very far located regions if the magnitude is 5.5, but in the epicentral area, if the magnitude is 5.5, or the area which experiences the earthquake of 5.5, and if there is an ideal condition, then there will be liquefaction. Okay. So this is not to the scale, but it shows that okay, what will be the vertical displacement, that is the slip along the fault, and how much will be the area extent. Okay. So in short, if I just put in sketch, then what basically we are looking at is that suppose you are having an area which is displaced. Okay. So you have the plate which has moved, or the block which has moved up. Okay, this one. And so this will be your surface area. Okay, so this will be your surface rupture you're talking, or we can say surface faulting. In terms of the length, and this will be your slip, but this is in height, but usually the slip has been measured along this one. Okay, so this will be amount of slip you see. Okay, this is the height, but this one will be the net slip actually along this one. So that is what has been shown here, that 3 meter and length is 4 kilometers. So this will be showing you length, and this will be showing you the height. Okay, or the slip. Basically, I would say better I call this as a slip. Okay, so one can expect 20 to 25 meter of slip if you are having magnitude greater than 9.2. Okay, or 9 magnitude we can say. And in 2004 Sumatra, the rupture, surface faulting, or maybe we can say the surface rupture, was almost 1300 kilometers. Now coming to the part of 2025 March 28th earthquake of Mandalay, that is Myanmar earthquake in Burma. Now this area is having this fault is known as Sagaing fault, and this Sagaing fault is almost 1200 kilometers long, which is the result of the lateral movement between two plates, that is your Indian plate and your Eurasian plate. Of course, many people say that there are few microplates which are also playing an important role, but mostly what we see is that the deformation is horizontally accommodated along between the two plates, that is the Indian plate and the Burmese plate, and this fault is named as Sagaing fault. So the magnitude was 7.7 and the rupture was almost like 500 kilometers, and the epicenter was located at the shallow depth of 10 kilometers. It was not very deep, it was very damaging. Okay, let us see a few more things over here. Now these are the maps on the Google. Also, if you go on the Google Maps and try to see this part, you will be able to easily identify a very straight fine line, but that is not man-made, that is because of the plate motion, okay, or the plate tectonics. So this is the trace of the active fault, that is Sagaing fault. And if you see the history of the earthquakes, there are many earthquakes which have triggered in the past. Okay, so this is the history of that. Okay, and mostly these earthquakes, why we see such a good record, because the recurrence is not very high. One, second, they are mostly the earthquakes which are been seen here either they are in 19th century, 20th century or 21st century. 21st century we had recently. So mostly the earthquakes which you see are in 19th century and 20th century. So there is like based on the GPS studies and the geological studies, it has been inferred that there is a slip on this fault in on the, if you say the rate, okay, is around 20 to 23 millimeter per year. Okay. And if you plot the microseismicity on this region, then you will realize that what is there is a typical pattern which has been, and this area is northeast area of Indian side. Okay, you have Imphal, Aizawl, so Chittagong, and sorry, this area. So you have Dibrugarh is also there. So we are in that periphery, and then adjoining region is your major active fault. So it ruptured for almost that. This was the intensity map. This, if you can see that the maximum intensity which has been shown here, almost like it has reached above 10. Okay, so very high intensity, extreme. Okay, very high, which has been seen along the fault. Okay, so this was the rupture was almost like, as we have mentioned, 500 kilometers. Okay, so this area, the 500 kilometer of length was been affected. So Sagain fault, as I told that this is what we are going to learn in this earthquake geology course, is that we will identify and we will learn to identify these earthquakes, how and where these earthquakes have occurred, and whether in some regions there are no earthquakes. And this exactly what happened here is that this 2005 occurred in a gap area. Okay, that is what they call seismic gap. Okay, so for example, if you are having these are the earthquakes 1930, 1929, and then you are having another set of earthquakes which are occurring over here. So this portion is your like gap area. There are no earthquakes. Like the last earthquake was in 1912, but if you see the pattern, they are very closely 10 years or 20 years or 30 years of gap is there. Okay, and the earthquakes have been occurring. Okay, so only 1912, and then there was 18, and that is a question mark whether that is not confirmed, but people think that there was another earthquake here. But this 2005 or 2025 was in this area, and that is what they call the seismic gap region. Okay, so 2015 2025 rupture appears to fill part of seismic gap that existed between your 1929 is this one, okay, and 1956. So this was the area which was ruptured in 2025. So even one can predict that, okay, fine, there is no earthquake in this region, and this has been the area of seismic gap. Okay, so one can expect earthquake in this region, and that is what the importance of the studies what we are talking about, the active tectonics and paleoseismology and earthquake geology part. Okay, so this was the effect of this earthquake far away in Bangkok region. Okay, and there were many buildings which got affected, completely ruined. Okay, new buildings were damaged, and I will come to this pattern of deformation, or not deformation, but the damage which you see, okay, over here, that why this happened. Okay, later on when we are talking about the seismic waves. Okay, and whether this is the ideal way to construct the buildings. You can see the sway of these buildings very clearly. Okay, So damage was extensive in this region, along the Saugeen Fault, away from the Saugeen Fault, and that what we call on fault, primary rupture, and secondary. Okay. There was another very shocking part which we learned was that the international airport has been constructed exactly along the or very close to the fault line. Okay. So with this topic, we end here, and then let's see about the Indian part. Okay. Now, as we have been talking about that we are cordoned by three sides. This is one. We have number of earthquakes, and last one was 2015. And the earthquakes which are listed from 19th century and even in 16th century, 20th century, and 21st century. The historical records also talk about the earthquakes which have occurred in 13th century also. Okay. Now, we have good records of these earthquakes, but we miss many such like evidence of such earthquakes, large magnitude earthquakes from this region. So, we are to some extent we are not having incomplete data set. But for designating this region as an vulnerable area from the earthquake hazard, this is more than enough for us to talk about that this area is capable or have potential to trigger earthquakes of magnitude greater than 7.5 and even greater than 8 or less than equal to 8.5. Okay. Then we have another area which is sitting here. This is your Andaman and Nicobar region. Again, the historical data set talks about that there were earthquakes in the past, and this is few of the earthquakes are been listed here are based on the geological studies, and these are the earthquakes which have been recorded by Britishers. Okay. So, there were earthquakes, bigger, large magnitude earthquakes during 19th century, and the last one was 2004. Then another part on the west of the Indian side is your Makaran subduction zone, which triggered earthquake and tsunami in 325 BC and 1945. And then comes Kutch here, again has an history of triggering large magnitude earthquakes right from 17th century, and the recent one was in 21st century 2001. So, to have an understanding of the past earthquakes, okay, this is what we call paleoseismology. Okay. Paleoseismology is the like we are talking about the ancient earthquakes. Okay. So, if you look at the time scale, geological time scale, then the portion in which we are interested in is this one. Okay. That is your Holocene epoch. It's the youngest portion of the period what we call Quaternary period. And this goes back up to 10,000 years. Because most of the industrialization and everything was during this period. So, if we look at the terminologies related to the faulting activities, then we have like if we say geological age, which again we can say era, period and epoch. So, we are looking at the Holocene, and that is 10,000 years. And in terms of the fault activities, if we have to classify that, then this is the area, but this is the part which we call the active faults. Okay. So, any faulting or any deformation which has occurred in past 10,000 years, okay, then we term that as an active tectonics. Okay. But if we go further in the older part, okay, then we say that potentially active, and much more older, then we say they are inactive. Okay. So more or less this is what we call the dormant faults, which are not going to be harmful to us, not going to produce any earthquakes. Okay. But in 10,000 years, if you have to talk about and further recent, okay, that what we have seen in the case of your Myanmar, and even the earthquake records what we have from Himalaya, Andaman and Kutch or subduction zone, Makran subduction zone, that falls into the category of active tectonics. Okay. And this is what we call the fault activity. If you want to classify, then these have been termed as active faults. That is your 10,000 years. So further, if we look at into this, that the paleoseismology, now this is a branch of geology where we study prehistoric earthquakes or old earthquakes, those have not been recorded, okay, by instrument, or those occurred during last 10,000 years. Okay. So this is the before the era of the instrumentation which came in. Okay. So paleoseismology supplements historical and instrumental record of seismicity by characterizing and dating large prehistoric earthquakes. Okay. So why it complements or supplements the instrumental records? Because what the activities which are taking place now, the earthquakes, okay, we know that pattern of earthquakes, and if we look at the historical data and the paleoseismological information which has been generated, that is a paleo earthquake, if we characterize that, so that will help us in dating the large earthquakes, and also helps in categorizing the seismicity as well as the faulting which is taking place in that region. Okay. Now significance is it mainly deals with the study of the formation of landforms and sediments. Okay. Because the information is preserved on the landforms, because we were talking about the surface ruptures. So deformation is coming right up to the surface and it is deforming the sediments, okay, young deposits. So the information we can gather from the landforms as well as subsurface, that is the surface as well as subsurface, that is your sediments. Okay. It also helps us and give us the knowledge of when, where and how big. Okay. So when, where and how big and how often the large earthquake occurs in crucial areas, and that goes without saying that this is for seismic hazard assessment of the region. Okay. It seeks to decipher the history of large earthquakes along individual faults and throughout a region over hundreds to tens of thousands of years. Okay. So it helps in building up the history of the earthquakes, of large earthquakes on that. Okay. So for earthquakes of past several hundred to several thousand years, paleoseismic studies complement the historical and instrumental data. So with this, I'll stop here and we'll meet in the next lecture, completing this topic and getting into the new topic. Thank you so much. Namaskar.